last day, we started looking at types of forces. We first of all spent some extra time looking at the force of gravity. Calculated by, well, every force is calculated by going ma, but in this case, since we know the acceleration due to gravity, I used the symbol little g for it. Don't try and write this down that fast. We said the force of gravity is mg. Another word for gravity is weight. What's another word for gravity? Weight. Your mass is not the same as a force of gravity. Your mass is a mass. It's measured in kilograms, and all forces are measured in newtons. Your mass doesn't change. No matter where you are in the universe, you'll have the same mass. And your weight will change. It all depends on what planet you're standing on and how hard it's pulling you back down. That's why we said your weight on the moon will be less than your weight on the Earth. But your mass won't change. We talked about this thing called the normal force. It's what we used to call the force from the ground. We said from now on, Zach, if you're pushing against a surface and Newton's third law is kicking in, the surface is pushing back, that pushing back force, we call that the normal force. Symbol Fn. We use the word normal because normal is a mathematical term that means at right angles to. So all of you, dead serious right now, take your non-writing hand and press down against the table. Hard. Are you applying a force to the table? What's the table doing? Applying the same force back. We call that force back the normal force. The normal force. If I push against a wall, what does the wall do? Pushes back against me. We call that force, the magnitude of the wall pushing back against me, the normal force. I will never give you an equation for the normal force. There isn't one. What I will do is tell you how you can calculate how big it is from a good free body diagram. This is a reactive force. It comes from Newton's third law, which was forces come in pairs. And it was also important for another reason. Ladies and gentlemen, what does a bathroom scale measure when you stand on it? Does it measure your mass? No, why not? Because when Tato did deep knee bends, his mass wasn't changing, but the scale was moving. Does it measure the force of gravity? No. Why not? Because when you did deep knee bends on the scale, the force of gravity wasn't changing, but the scale was moving. Folks, what does a scale measure? Normal force. So when I ask you in a question, which I will, what does a scale read? What I'm really asking you to find is which force? Normal force. Okay? Put your pencils down, look up. We went on a big rant. I said that a scale measures normal force. We said that any good amusement park ride does not change gravity. What force does it muck around with? All it does is it mucks around with your normal force. It makes you feel lighter because what all of you right now think of as your weight is actually when you're standing, the ground pushing up through your feet, or when you're sitting, your chair pushing up against your body. Make that lighter and you'll freak out. Make it heavier, you'll also freak out, but not quite as much because an increased normal force, any of you that have played on a playground and gone on a swing have experienced at the bottom of your swing an increased normal force. We'll actually look at that free body diagram in Physics 12, but there you're moving in a circle, and that means winning. Rylan is looking over, yeah, we're doing that right now. Circular motion is a little bit different from going in a nice straight line. Okay? I think I showed you a video of a kid experiencing his first changing normal force. Yes? We watched the video of the kid on the roller coaster. Those of you that were away, you missed a great day. Lots of cool videos. Oh, I also said, now, for all of you, example 1, an elevator question is going to be on your test. In fact, it'll even be more blatant. There's probably going to be a question where you're accelerating upwards. There's probably going to be a question where you're accelerating downwards. Hand it in the appropriate block. Thanks, Justin. So there's absolutely going to be an elevator question in your future. And now we're going to talk about another force, the force of air resistance. Air resistance, and I've said this before, Alec, but it bears repeating. Gracie, air resistance is a really difficult force. Did I give you the notes? I did? Okay. Air resistance is a really difficult force because it changes all the time. If you've ever stuck your hand out of the window of a moving car, hopefully you've noticed the faster you go, the more air resistance. The slower you go, the less air resistance. It's actually the force of air molecules bumping into an object as it's moving through the air. And I did use the air cannon the other day to show you that air must have mass because it can apply force. Okay, here's the key. The force of air resistance always has direction opposite to motion. So we're going to draw force free body diagrams for 3 situations: a ball being thrown, and then on its way up, and then on its way down. So part A, we're going to be talking about right now as I'm accelerating it upwards, but before it leaves my hand. So part A is this part. Part B is on the way up, right there. Part C is, without hitting the ceiling, on the way down. Okay? We're going to do one of these at a time. First of all, we're going to pause for a second. Alrighty. So, part A. You know what? Let's do our free body diagram right on the ball. We'll go like this, right there. What are the forces acting on it? Get the obvious one. Absolutely. Absolutely. But look up, look up, look up, look up, look up. When I do this, which way is it accelerating? Upward. So which way must there be a bigger force pointing? Up. Has to be. What force is that? We're going to call that the force of the hand. You could call that a normal force because the hand is sort of a surface, and I'd live with that too, but something is pushing it upwards. By the way, I can also, just hang on a second, Connor, I could also have it going up. If I did the normal force, the force of the hand less than mg, look, 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 watch, 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 watch. I know I must be going faster because the ball left my hand. I know the acceleration has to be bigger, because if I don't make the force up bigger than gravity, the ball won't leave my hand. Connor, you had a question.
Will you take marks off if we use the arrows like the same way?
Yes, absolutely. Because the arrow lengths tell me that you've realized which force is bigger and which force is smaller. Absolutely, I will. Okay? That's why I said I'm going to be fussy, roughly to scale. Roughly, show me which one's bigger. Now, there is, I guess, technically air resistance while I'm throwing it up, but I'm going to pretend that my hand is covering it and I'm getting all the air resistance on my hand. I don't want air resistance in this diagram. Okay? B, it leaves my hand on the way up. So, oh heck, let's label the ball again. What are the forces acting on the ball while it's left my hand, while it's on the way up? Get the obvious one. Yep. What else? What does it want me to include according to part B? Now, what does it want me to include according to part B? Air resistance. Which way is the ball moving, traveling? What direction is its velocity? I'm looking for a 2-letter word, begins with letter U, up. So which way is air resistance if air resistance is always in the opposite direction of motion? Yeah, and I'm going to put it right beside here. How about right there? F, air. And I'm pretty sure air resistance is smaller than gravity. It's there, but it's not something we need to take into account all the time. What about part C? What are the forces acting on this ball on the way down? Get the obvious one. Gravity. What else? What does it want me to include? This time it wants me to include air resistance. Which way will I point air resistance this time? Little short arrow pointing up. And this is what I mean, Connor, by would I be fussy? Yeah, absolutely, for something like this. If you did it the same size, that would mean somehow the ball was hovering or going at a steady speed, not speeding up. If you did air resistance bigger, it would have to be accelerating up, which does happen right when I pulled my parachute. I mentioned I jumped out of an airplane. When I jumped out of an airplane, right when I pulled my parachute, air resistance was larger than mg. That's what slowed me down. But then eventually you hit an equilibrium point. Mr. Dueck? What while? How can the ball be going up in part B if all of the forces are pointing down? Yeah. Yeah. Well, even more basic than that, I would say this. Velocity and acceleration don't have to be in the same direction. Velocity and acceleration do not have to be in the same direction. For example, when you hit the brakes in a car, What direction is your velocity? Forwards. But when you're hitting the brakes, what direction is your acceleration? It's backwards. And this is one that really bugs kids because last lesson on free body diagrams, when we looked at in our notes at the very end, the free body diagram for an inline skater dragging their foot, you might recall a lot of people wanted a force pointing forwards because the skater was moving forwards. And I said, no, 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 no. Velocity and acceleration don't have to be in the same direction. You can be traveling forwards and accelerating backwards. We can call that slowing down, which means, hey, you didn't need a force pointing forwards. You don't need one there. You don't need a force pointing up for the ball to be traveling on its way up as long as it's slowing down. As long as it's slowing down. In example 6, actually in part 4C, if the falling ball is speeding up, write a net force equation. I've scrolled down, but you have the free body diagram from part C. Who's winning? Look at the picture. Who's winning? Really? Yeah, right? Longer arrow. By the way, Connor, that's also why, because if you do the arrow lengths longer and shorter, when I ask who's winning, it's pretty obvious. See the picture, C4C? Which is the longer arrow? Look at 4C. Which is the longer arrow? 4C is right here, is it not? Like it's right here, right above. I just had to scroll down. So you got for part C, the little ball picture there? Yes?
I think I'm on that.
Okay, Connor, right here. We just did it. Right here. Right here. Yep. Which is the look up, look up. Which is the longer arrow? More specific. Yes, which is the shorter arrow? I'm going to ask you the same question. I'm just going to phrase it differently. Who's winning? Who's losing? There's my equation. That's why I'm fussy on the arrow lengths. It cuts that down. Figured out where we are now? Yes? Sorry to pick on you. Winner minus loser equals MA. And in fact, if you, Brisa, gave me more information, I could calculate air resistance. I think I'd do that in the next one. Let's find out on the next page. Oh, yeah. A 90-kilogram parachutist free falls for a time and then opens a parachute. His new upward acceleration is now 1.5 meters per second squared since he's slowing down while having a downwards velocity. He's moving down, but he's slowing down, so he must be accelerating up. Gio, what does part A want me to do? Yeah, free body diagram. I'm never going to type that again. FBD. Okay, draw a free body diagram. All right, how about over here? Let's do part A. There's the parachuter. Have I mentioned that I jumped out of a plane? What are the forces acting on this parachutist? Get the obvious one. I agree. What else? Air resistance. Which way? Upwards. Bigger, smaller, or the same size as mg? Let's see. What direction is this person accelerating? Upwards. Which way must the bigger force be pointing? Which one? Down or up? Ready? What direction is this person accelerating? So which way must the biggest winning unbalanced force be pointing? What law is that? Newton's first. It's Newton's first. So I'm going to ask you again, air resistance, bigger, smaller, or the same size as mg? Has to be. What's my equation? Who's winning? Air. Minus. Who's losing? Equals. There you go. I'll say this again for the umpteenth time. Max, don't try and memorize all these equations. With a good free body diagram, which comes from your understanding of Newton's laws, you can derive any equation out there. Ryland is in Physics 12. Have I taught you anything besides Newton's laws and winner minus loser? Nope. Then we just went slanty and brought in some trig, but it was the same equations. Okay. Part C. What does part C want me to find? How would I get the F air by itself? Is that okay, Alec? Yeah? Air resistance is going to be mg plus ma, or ma plus mg. M 90, yes? G 9.8, not negative. We took care of that in our winner minus loser shtick. Minus M 9, no, minus plus, Mr. Dewick. I'm looking at the equation above. Plus 90 times, did they tell me the acceleration? 1.5. What do you get? Do this one in your head, Mr. Dewick. Well, it's going to be really close to 1,145. It's going to be a little less than 1,145. It's going to be right around 1130. Double check me. That's an estimate. I didn't do that one in my head. I made a good guess. What do you got? Okay, people, I'll race you. 90 times 9.8 plus 90 times 1.5. I said 1,100. Oh, I'm a little lower. Wow! Way off, Mr. Dewick. Why am I so far off? It's 90 times... Oh, because it's not 1,000. It's 900 plus 150. Good gosh. Do you get 1,017? Wow. I'm going to go to 3. How many sig figs should I go to? I guess 3. Well, 2. You know what? Let's go 1,017 units. Because it's a force. Air resistance, however, is really, really challenging. Because which way is this person accelerating? Up. So what's going to happen to their downward speed if they're accelerating up? And they're slowing down. So what happens to air resistance when you slow down? It gets smaller, which means now you're not going to be accelerating up as fast. You're going to be slowing down. Air resistance gets smaller. Gravity starts to take over. Eventually, you reach kind of an equilibrium point where gravity exactly equals air resistance. A parachute lets you do that at a survivable speed. Oh, there you go. The force of air resistance is actually not a constant value. In fact, the force gets larger as speed increases. A falling object will eventually reach the point where the force of air resistance equals the weight. Remember, weight is another word for what? Of the object. And at this point, we hit something called terminal velocity. Terminal velocity also depends on your cross-sectional area, how wide you are. That's why skydivers, when they free fall, assume that classic spread-eagled free fall position. If they want to go faster, if they tuck and go vertical, like when you cliff jump, their terminal velocity will be much higher. And then all a parachute does is it massively increases my surface area so that my air resistance force is big enough that it brings me to a much smaller terminal velocity. Kind of like this. Put your pencils down, look up. So let's continue on here. Turn the page. Example 8. A parachutist jumps out of an airplane and free falls. I mentioned I jumped out of an airplane. They reach terminal speed, and they reach that speed for a while. They then open their parachute and quickly reach a different terminal speed and descend to the ground. Sketch a speed versus time graph. By the way, the reason I kept saying speed is if I had said velocity, what direction are you traveling the entire time when you're jumping out of an airplane? Yeah. And so if I did that, we would have to be negative below the x-axis all the time, and I just didn't want to do that. So we're going to sketch a speed versus time graph. This is going to be a really rough sketch, and it's a sketch, not a full graph. I'm not going to put a title. I'm not going to label it with a scale. Just a sketch. When I'm sitting in the airplane before I jump, what's my vertical speed? So there should be some amount of time where my speed is 0. Now, really, that should be like 15 or 20 minutes long, however long it takes to get to the altitude properly, but we'll just draw a short chunk. Then I jump. Ah! What happens to my speed? What happens to my speed? Gets bigger. So let's suppose my new speed is right there. Now, I have a bit of a question. Don't write this down. See, I don't think it looks like this. When is air resistance at its minimum when I jump? Right at the beginning. So when am I accelerating maximum? Right at the beginning? And the slope of a speed time graph is acceleration? To be honest, if I'm going to be fussy, I think it would look something like this. And then it would level off, and this is my terminal speed. The faster I fall, Matt, the bigger air resistance gets, Matt, the smaller my acceleration. And where does acceleration appear on this? Remember from a couple units ago? As a slope, so the less my slope. I free fall for a while, and then I pull my parachute. Woohoo! What happens to my speed when I pull my parachute? Pardon me? Goes down, I agree. When is air resistance at its biggest? Okay. I think it's going to look kinda, I got to think about this here. I think kinda something like that. I think. Maximum air resistance, maximum slope right away. Minimum air resistance. In fact, now here's the problem where my graph breaks down. When I jumped out of an airplane, I mentioned I jumped out of an airplane, this part here at terminal velocity with the parachute open actually lasted about 5 minutes, which really means if we were doing this graph to scale, we should do that. I'm not going to. So my time scale is going to be terrible. Okay? It just is. I drift for quite a while. You can say terminal V, comma, shoot open, right there. I drift for quite a while, and then eventually I hit the ground. What happens when I hit the ground? Something like that. I always make the joke that it sort of looks like the side view of an old VW Beetle. Sort of. Not quite, but sort of. Is that okay, Max? I've convinced you. I think roughly that's what it would look like. There might be some fine-tuned differences, and my time scale is garbage, but it would look something like that, I think. What's your homework? So you can now do, if you haven't already, Section A. I had initially assigned Section B, 1 and 2. Now, I can say we can also do number 3. 4 is good. 5 is good. 6 is good. 7 is good. Yeah, I'm probably going to assign, I'll skip 8. 9 is good. 10 is good. 10 is a thought question. Answer is going to be at the end of the homework. 11 is good. It's also a thought question. Answer is at the end of the homework. 12 is good. 13, 14. And then there's some of the answers as well. We are heading into a 2-week break. For those of you that were away last week, I said that for me, term cutoff is going to be the first Monday after we come back. That means if you owe a number of assignments, if you have a number of assignments missing, there is a good chance that you might get an email on Friday politely asking your parents to ground you for spring break until you're all caught up on your homework. Oh, you're welcome. Don't thank me. Don't thank me. So part of that, though, I'm giving you a full half an hour to get stuff done today. This is your chance to finish this and any other missing assignments. On Wednesday, we're going to be watching a Mythbusters video, a very cool one, and performing a very cool experiment using notebooks that I purchased from Staples.